So thus far in our CAM discussion, we've talked about the SVAJ diagrams, but we haven't gotten to the point of actually saying how big should my CAM be, how large should my roller follower be. That's the focus of what we're going to talk about today. Now, it seems relatively straightforward, and it is, but there are a few areas that need specific attention that can otherwise result in a poor CAM design. So that's what we're going to focus on. So we're going to start off with our SVAJ diagram that we've been generating. And again, remember our fundamental law of CAM design is saying that we want to match position, velocity, and acceleration between all of our segments such that they are continuous. And we can have steps in our jerk, and that's all right. Now, we're going to take those profiles and turn them into a CAM sizing. Now, before we do that, we need to go through a little bit of terminology. And the focus of this is really looking at the pitch curve, which is our S profile that we are wrapping around our base circle. Or actually in this case, a prime circle because we have a roller follower. So our prime circle here is shown in the circle that would be have this center right here. So that would be our prime circle. And you'll notice that that comes out here beyond the surface of the cam, and that is then the center that the roller follower would follow. So what we do is we basically just take our S curve that we generated and we wrap it around that prime circle to form our pitch circle, or our pitch curve that we're interested in. And then we have to do an offset to figure out where is the cam actually going to be. So that's where we start with this. Now the other piece of terminology that I want you to be familiar with is an eccentricity, which is basically how much offset do I have between the axis of my roller follower, so that is this axis here, with the axis of the cam. And this offset distance right here is given epsilon, and that's referred to as the eccentricity. And what we'll do is we'll use that eccentricity to help shift our pressure angles, which is the complement of a transmission angle, so we'll talk about those momentarily. But we use this to shift those when we have an asymmetric cam design, which means if we have a steeper rise than a fall or vice versa. So we can use that to our advantage. The other terms that I want you to pay attention to are just the radius of the roller follower, as well as the radius of the base circle, which is the circle wrapped around the physical cam, and then the radius of the prime circle, which is where the follower is moving through. All right, so with that terminology, let's talk about what are we concerned about in cam design. Three primary pieces. One is what's the pressure angle, and this is the complement of the transmission angle that we've been talking about from linkage design, so fairly easy to understand, 90 degrees minus that. Then we talk about the radius of curvature of the cam, and we talk about that relative to the roller follower that we have tracking it. And we want to make sure that we have our roller follower tracking the cam properly, and if we have problems with our radius of curvature, we can have situations where we won't follow the S profile. And then once we move beyond this, then we start to consider things like contact stresses and how much force is being applied between or within the cam joint, and whether or not we can handle those contact or Hertzian stresses. We can then move into things like dynamics as well as material choices. So there's a number of other things, but the three ones with this first pass of cam sizing is looking at pressure angle, radius of curvature, and then contact stresses and forces. All right, so let's attack the first two. So first of all, pressure angle. Pressure angle here is the difference in angle between the axis of motion of the follower, so that is the green line here. That is the axis of motion of the follower. And we are comparing that to a common normal here, or the axis of transmission, and we look at the intersection between the roller follower and the cam joint, and then this defines our axis of transmission. So we can then go about defining this from the actual physical geometry of our system. And you'll notice here that in the numerator, we have the velocity. Subtracting from the velocity, we have the offset, or the eccentricity of our cam. And then in the denominator, we have position as well as the roller follower radius and the eccentricity. Now, what dominates this is the velocity in the numerator, and we'll see this just momentarily. Now, what do we recommend as far as a radius for this? Well, just like we did with cam design, where we said this depends on whether or not we have a pin joint or a slider joint. Now, very often we have a translating follower, which is the equivalent of a slider joint. And for those slider joints, we recommend keeping the pressure angle under 30 degrees. And again, this is the complement of the transmission angle, so it's similar to saying I want to keep my transmission angle greater than 60 degrees. Same idea. Now, if we have an oscillating follower, we can push this up above 30 degrees, maybe 35 or 40 would also be acceptable. So we have to pay attention to this pressure angle. All right, so If you recall, in a previous video lecture, we had talked about generating a polynomial profile for a rise, fall, dwell cam. And we developed a polynomial for that profile. That's the cam design that I have here on the left. So you can see the S profile, the velocity, the acceleration, and the jerk for this profile. And again, we're continuous all the way through the acceleration, and then we have discontinuities in our jerk. So let's look at the pressure angle as a function of the cam rotation angle for this specific design. So I've gone ahead and picked an eccentricity of 0, and I've picked a prime circle radius. And this now is the pressure angle plot for this cam design. Now, one thing that you'll notice is in this design, I am under 30 degrees, which is desirable. And because I have no eccentricity and because we have the same duration for our rise and our fall, we have symmetry as far as the magnitude of our pressure angle in the positive and the negative direction. So I don't need to use any eccentricity to help offset this in this specific case. Now, take a step back and look at this pressure angle plot, and then look at the SVA and J diagrams. And one thing that you'll notice, as I was mentioning before, the velocity in the numerator of this arctangent function really dominates. So when you look at the velocity profile, it has a very similar shape to the pressure angle profile. So that's where you can see that dominant behavior occurring. All right, let's move from pressure angle to radius of curvature. So radius of curvature, we're focusing right now on the pitch curve. And we can say that every location or every point on the pitch curve has a radius of curvature. Or basically, where can I draw a circle that is tangent to the cam at that one location and then find what is the radius of that circle. So let's look at this at a few different locations. I can first of all look at it up near the apex there where I have this purple circle, and I can measure the radius of this, and this would be the radius of curvature up at that point. Similarly, we can have a much larger radius of curvature near the contact location between the roller follower and the cam joint. And we can then do this all the way throughout the entire cam, and we could plot what that looks like, and that is our radius of curvature plot that we'll be looking at in just a moment, or a radii of curvature. Now, why are we paying attention to this? Well, we ideally would like to keep this radius of curvature much smaller than the roller follower diameter, and the reason for this is then it makes sure that our S profile is tracked, and I'll show you what I mean by that in just a moment. But before we get there, if you dig out any calculus book and look at curvature, here is a mathematical definition of curvature. I won't get into the derivation of it, but that is provided in any calculus textbook. And we can just then use that. But you'll notice that we've got the prime circle, we've got the S profile, the velocity profile, all built into this, as well as the acceleration profile in the denominator. So we're looking at derivatives that are defining the curvature of our cam. All right, so what are some issues that we can run into with our radius of curvature? So the first is looking at undercutting with a negative radius of curvature. So in this case, I happen to have a roller follower that has a fairly large diameter, or large radius, but a very small radius of curvature right at its contacting location. So if we look right at this location right here, you'll notice that I have a smaller radius of curvature of my cam relative to the roller follower. And because of that, I'm not going to be able to track that S profile within that small radius of curvature with this roller follower. So this concavity I cannot track. This is called undercutting. Another example with a positive radius of curvature would be what I'm going to show here in the bottom, where right in this left plot, we have the same radius of curvature for our S profile as we do for the radius of the follower. And we happen to have a cusp point where my cam comes up to this sharp point right here. And you can imagine the roller follower would just be tracking along and kind of rocking right over the tip of that cusp. So that would be a bad situation because we'd have very high contact stress. Now, if I push this even farther by decreasing the prime circle radius, you'll see that we get to another undercutting condition where I actually have material that would otherwise need to be there for me to follow my S profile, but is getting removed by the fact that I have a cusp. So this is another situation where too small of a radius of curvature on my cam results in undercutting. And again, this is now for a positive radius of curvature. So both of these being issues that we need to manage and deal with. So how do we deal with it? Well, we just make sure that the radius of curvature of our cam is much greater than the radius of curvature, the follower radius. And we usually say a factor of 2 to 3 is desirable. So that's where we want to start. So we'll start with this S profile here for the same polynomial function that we had looked at previously. And now let's look at the radius of curvature for this specific cam. So I've picked a case that's a little bit more extreme than what we would ideally like to build to illustrate this. So what I've shown on the right here is actually a diagram of the cam with the roller follower at many locations around it. So the center of my cam is this little blue circle right here. And then I have my roller follower, this red circle, with then the axis of translation being shown right here. So this is where the follower would be moving back and forth between. And then all of these black circles that surround it, those are the locations of the roller follower at positions around the cam. So you can see as I would move upwards to the top here, I would have the, that would be the rise fall segment, and then through the bottom that would be my constant dwell segment. So let's look at what the radius of curvature is for this cam. So here's our radius of curvature for this cam, and you'll notice that we have the first segment where we're getting a lot of oscillation of this radius of curvature, and it's swinging from negative to positive and back and forth. So what's going on here? Well, you'll notice right around, maybe 10, 15 degrees, we're getting a negative radius of curvature, which corresponds to this area right here that we can see the same negative radius of curvature. And then we flip over, and there's actually no points along this vertical line segment. Instead, it's jumping from a negative value all the way up to a positive value. And then we're getting positive curvature, which then kind of comes down to a smaller value, jumps up again, and then goes negative again. And that's what we can see here on the top, where we have our radius of curvature changing along here. Here it's fairly low, here it gets smaller. And then as we go through our dwell segment, we have a constant radius of curvature, which is right here. So what I'm interested in is what is the absolute, the minimum value of the minimum absolute value of this radius of curvature. So here I'm showing the minimum positive value of 0.86 and the maximum negative value of minus 1.5. Now this is relative to a roller follower that I believe is 0.2 diameter. So in this case we are satisfying that 2 to 3 requirement, but we have other problems with this cam in terms of pressure angle. So just an example of what this radius of curvature looks like and how it can swing from negative to positive based on what our curvature looks like. All right, so we've got all of these things to start to build a cam. How do we start? What are some ways that we can do this relatively quickly? And here are some rules of thumb to help us along. So first of all, start off with a prime circle radius. This is for the cam. That is 3 times the lift of the cam. So in the situation that we have synthesized here for that S profile, we had a lift of 1 inch. So that means I'm going to start with a prime circle radius of 3 inches, just as a place to start. And then I'm going to go ahead and compute the pressure angle for all values of theta, and theta is the cam rotation angle. And then I'm going to iterate to keep that pressure angle less than 30 degrees. So what am I going to iterate? Well, I'm going to both change the prime circle radius and possibly use eccentricity to correct for any asymmetry. And this means that I might have a more aggressive rise than fall or vice versa. Therefore, I can balance my maximum and minimum pressure angle. Then I'm going to move on to checking the radius of curvature. And I'm again going to be looking at the minimum absolute value of the radius of curvature relative to the roller follower. And here I'm going to again have to iterate possibly on my prime circle radius, but maybe I can just do it through resetting the follower radius to help me get to a decent radius of curvature. Now another thing I have to pay attention to is as I make my roller follower smaller, my contact stresses go up, and so I have to kind of play this game. So you might notice that all of these values improve as I make my prime circle bigger. So you might say, well, why not just make it bigger and bigger? And the reason is because as it gets bigger, we have more mass and more package space, and it just becomes a little bit more challenging to put this into an actual machine and to pay for it because it gets more expensive with the size. So the 2 equations at the bottom are the ones that we're really paying attention to. So let me now move from this to actually doing an example in MATLAB so you can see how this works in an iterative fashion. All right, so I'm in my MATLAB code now, and I've written a script M file that allows me to size a cam. So the first piece that I have as an input to this is the polynomial function that I created previously. So I've generated that previously, I bring it into this, and this program that I've written allows me to have 4 different segments. In this case, I only have 2 segments. I have the first segment that's the rise fall, and then a second segment that's purely a dwell segment. So those are my 2 segments. Each one occupies 180 degrees. So what I'm really interested in terms of sizing is I'm going to set up what the base circle radius is. So I'm setting it to 3 in this case. I'm setting what the roller follower radius is, so half of an inch in this case. And then I can set my eccentricity. And I know I'm not going to need any eccentricity for this symmetric curve S profile that I have. I can then calculate the prime circle radius, And then I move into defining what the length of each segment, and again I said my first two segments are each 180 degrees to occupy the entire profile. Then I scroll down and I'll show you a few more pieces of this. First of all, I'm bringing in just polynomial coefficients, and so I can then take my S profile and take the derivative, get the velocity, the acceleration, and the jerk, and I do that for all the segments, and again I allow for 4 different segments. So that's what all of those are. And then I set up a dimensionless variable to allow me to do the theta over beta conversion. So that goes from 0 to 1, and that's then where I generate my SVAJ profiles for the different segments that I'm going to add together. So I'm taking each one of those segments and concatenating it with the next segment. Then I create a theta variable just to allow me to do my counting, and then I go ahead and plot my SVAJ diagram. So that's what's going on here. So I'm plotting, have 4 different subplots. And then I move into calculating my pressure angle and my radius of curvature. Again, the same equations that I showed you and you can dig out of your book. I then plot the pressure angle, I plot the radius of curvature, and then finally I plot the cam profile. And the way I do this is I basically just look at what are the positions of this in Cartesian space and then use my rotation operators that we've used previously, and that's what this cosine of theta is doing in the sine of theta. And I plot those, and I use these circle commands, which is basically a couple of functions that I have built in here that are using the rectangle command to create circles for all those locations. So let me run this first of all, and again, this is where I have a base circle of 3, so this will be a fairly mild cam that I'll be creating, a fairly large diameter. So when I run it, you can see my SVAJ diagrams on the left here. Again, my S profile is showing just the rise, fall, and then dwell segments. My velocity and my acceleration are all continuous. I have discontinuities in my jerk at the 2 ends of it. And then I move over here and let's look at the lower right now. And you can see in the lower right, I have a cam profile that is very gentle. You can see the roller follower there, and then also the translating element that's showing what direction it's moving. Now, the way that we typically build a cam or start to size it here is do a kinematic inversion. So we know that normally I would be taking my cam and rotating it and the follower axis would stay stationary. What I actually do to draw this and to usually do most of my analysis is I invert that and say, let me hold the cam stationary and now I'll move my roller follower axis around the cam sequentially. And therefore I'm going to move this follower axis in the positive direction, the counterclockwise direction. And because of that, you have to then think about the cam as rotating in the opposite direction. So the conventional cam rotation would be clockwise in this case for this design. So as it rotates clockwise, you'll see that it starts to move up the rise and then the fall. And then the last 180 degrees is the dwell segment. And then you can see I'm plotting the radius of curvature here. And you'll see that our radius of curvature, drops down to about 3 here, peaks out just at about 7.5. And then we're looking at our pressure angles too. And remember, we want to keep these pressure angles under 30 degrees. And I'm at maybe plus or minus 15 degrees. This is a very gentle cam profile. Now let me illustrate maybe a little bit more aggressive profile and also what happens with eccentricity. So I'll jump back here and let me make maybe a base circle radius of 1, and then I'll set up some eccentricity of how about 0.5, and maybe I'll make my roller follower just a little bit smaller, down to 0.2. So now when I run this, now you'll see that I've set up some eccentricity for my translating follower, so it has been offset in the positive direction. If I had a negative eccentricity, it would move in the opposite direction. I have now created some concavity here, some negative radius of curvature in my cam because of that, and we can see that up here in the radius of curvature plot. And now you can see my minimum positive radius of curvature is about 1, and so I'm still okay compared to the roller follower radius that I just set or just decreased. And I have now moved up my pressure angle here to 20 degrees on the positive side, but I'm above, maybe I'm up into 47 degrees, minus 47 degrees on the other side. And so again, as I said, that eccentricity, as we shift that back and forth, that is what will allow us to balance our pressure angles if we have an asymmetric profile. With this symmetric profile, now I have created a poorer pressure angle in one direction. Now there are some cases where we actually want to do that, and the cases where we would want to do that is if we're perhaps providing a large force to push it outwards, in which case we want a good pressure angle, and then maybe we just have a large spring force or just spring force driving it back home. We can usually then have a little bit higher pressure angles on the return stroke than we can on the extension stroke. So just some things we can play with. And you can imagine that I could iterate through this to get to what I think would be an acceptable or a good cam profile, where usually I want to keep my cam as small as possible while still having good values for the pressure angle as well as the radius of curvature, and to keep my cam dynamic, or the forces that I'm generating, reasonable. Our next step would then be to start to look at the dynamics of this and say, let me make sure I have enough spring force to keep this cam joint closed. All right, so let me jump back now to the PowerPoint slides, and we can talk about what happens when we go to a flat follower instead of a roller follower. So now let's take a look at that flat follower. So a flat face follower is looking something like this, where I simply have a surface that is contacting the cam, and you'll notice that the location where it's contacting will actually slide side to side as I move through the rotation. Now, the first thing that you might look at here is say, oh, pressure angles. Remember, we were looking at this pressure angle as the difference between really the normal where I'm contacting it compared to the direction of translation. And with a flat face follower, I have a zero pressure angle. This is great. Why don't everybody just use flat face followers? Well, you'll notice that where I'm applying this force is offset at a distance from the axis of the translation. So what we're doing is we're creating a moment on that linear bearing that is allowing translation, and sometimes we can create binding in that joint depending on how much offset we create. So we have to pay attention to this overturning moment that's being created on the follower joint. Now, the other thing that is unique about having a flat face follower is you can imagine going back to the radius of curvature discussion. If we have a negative radius of curvature with a flat face follower, there's no way that flat face could follow the concavity. So whenever we have a flat face follower, we usually have to make the prime circle a little bit, or the base circle in this case, a little bit bigger, such that we have no negative radius of curvature. So only positive radii of curvature that we can then follow with our cam design. Now, a lot of the equations in developing the flat face follower are very similar. We're not going to go into the details, but in your reading, if you're interested, you can dive into it. So let me just summarize now. What do we size the cam for? Well, so first of all, we focus on the pressure angle and then move on to radius of curvature. Those are really the only two that we paid much attention to today, but the next major step is to then do a force analysis and specifically look at the stress in the roller to cam interface. And to do that stress analysis, we need to know the distance that we're acting, or the distance into the page of the follower, so how wide is it. Also the roller follower radius as well as the radius of curvature throughout the range of motion. So we then be looking at the contact stresses. We then want to move on to dynamic force analysis, material selection, how do we lubricate it, things like that. Now, how do we tune these radii of curvature and the pressure angle? We use the prime circle radius, we use eccentricity to offset or to handle asymmetry, and we then also change the follower radius. And these two equations that I'm showing here are the ones that we really need to pay attention to as we're doing our cam design. And you'll find that it is a very iterative process to come up with a good cam design.